Hello, everybody, and welcome back. We are on question number 4, the very last question of our 2015 Gauss paper. And what does question 4 have in store for us? In the diagram, BCDE is a square of side length 2. Equilateral triangle XYZ has side length 1. Vertex Z coincides with D. And vertex X is on the line ED. What is the measure of angle YXE? So this angle here. Alright, that one's not too bad. They're sort of easing us into the question and the scenario, which is why it's a nice little light bulb question. There's 180 degrees in a line, and there's 60 degrees in an equilateral triangle. So in order to make up the full 180 degrees, we are missing 120 degrees. And that's really about it. I suppose if you wanted to write something out, you could say 180 degrees is angle YXE plus angle YXD, which is angle YXE plus 60 degrees, because it's an equilateral triangle. And so 120 is angle YXE, but there's not really a whole lot to do, which I guess is why this is a light bulb question. Alright, we've got B part. Do we have a... Yes, we do have a C part, and then the contest ends. So, and both B and C are written. So B, a move consists of rotating the square clockwise. So rotating it this way. Around a vertex of the triangle until a side of the square first meets a side of the triangle. The first move is rotation about X. And the second move is rotation about Y, as shown in the diagrams. So we pivot around X. Everything's moving clockwise. So the E starts to lift up and D starts to lift down, separating D from Z. And we keep rotating until E was about here, and now E has sort of rotated into position. D was here and has rotated into position. B was up here and has rotated into position. C was here and has rotated that way. And we will have rotated 120 degrees, actually, thanks to A part. Alright, so that's the end of the first move, and then, so Y is stuck in the vertex here. Y and E now coincide. And then we continue to rotate this. Yeah, we continue to rotate a little bit more now. We keep E fixed. Yeah, because the next rotation is about Y. And then everything sort of shifts around until EB lies along EZ. And then the next shift would be sort of the same as the first. We'd pivot around Z, and B would move out, and E would move there, until B coincides with X. Okay. So I'm understanding how this thing is going. In subsequent moves, the square rotates about the vertex Z. Well, that's what I just said. Then X, then Y, and so on. Determine with justification the total number of moves made from the beginning of the first move to when vertex D next coincides with a vertex of the triangle. Okay. So I can think of maybe two ways to do this. I think a quick shortcut way might be something like, imagine you're D, or imagine you're standing on D. What does it look like the triangle's doing? I know the square is what rotates during the question. But what does the triangle look like it's doing? Well, first it appears here, and then suddenly Y is now in the corner here. Y has actually moved to coincide with E, which is what I said a little while ago. And then the triangle moves so that that Z is in the middle here, and then the triangle rotates again. And then it flattens itself, and then rotates again, comes out here, and so it'll take 1, 2, 3, 4, 5, 6, 7, after the 8th move, D will be in a corner again. Now, I'm not entirely sure the best way to write that up. I think you probably want to start with some sort of argument that says, imagine you are on D, what the triangle is the one that appears to be moving while you appear stationary. But that's not necessarily the easiest thing to do. I suppose we could instead sort of draw a series of pictures. I know it's only going to take 8 moves. So move 1, rotate about X. And that's when we had our triangle there. That's equilateral triangle. And then we rotate about Y. So, Y, X, Z, X, Y, Z. So now we're going to rotate about X, again clockwise. So this will be the 3rd step. And so in the end, X, Y, X is going to be in a corner. And then after the 4th step, I should probably keep track of where D is. So here's D. And then D now moves down to here. D is still here. Oh, also, I've got this wrong. X, Y, first of all, Z's in the wrong spot. Z's down here. Y is here, but X will become... No, X will be in the corner. So X will now be in this corner, so the one opposite the corner that X will be in is now D. And then we rotate about X again. So draw my triangle, and now XY is the flat side. So D has only moved down slightly. For move 5, we rotate about Y again. And that'll be one of these full moves. So Z will coincide with this corner here. So we'll draw my triangle, X, Y, Z. Now Y stays the midpoint of that side. Now we're with Z, and once we've got that, we can draw the rest of our triangle. And so Y is in the... Y to D looks like that, so, and that stays the same because Y stayed on the midpoint of that side. That side just sort of rotated. Okay, we rotate about Z again. So draw X, Y, Z. And now Y, X. X will become the new midpoint of the line, and it'll move to sort of here. So D is here, and now we'll rotate about X again, and Y will be down where D was. So it won't take... Did I miscount the numbers? Oh, I counted the starting position as 1 step. Okay, so it does take 7 steps. So 7 steps, we rotate about X now. And so D comes up to coincide with Y. It's not a very equilateral triangle. Let's fix that a little bit. I think a picture is just fine. D coincides with Y after 7 steps. Okay. So that looks good. Now is that it? Is it D, or does it have to be coincide with D and then a line lies on DE? Because E should be here. Right. There's E. Oh, no, E's not there. E's down here, and then here, and here, and here. So E should be, yeah, E is here. Did they just want D in a corner again? First move when vertex D coincides with a vertex of the triangle. Okay, nothing about sides of the triangle and sides of the square lining up, nothing like that. Okay, so determine with justification. Well, a series of move pictures would do the trick just fine. Okay, it doesn't always have to be paragraphs and paragraphs of text. Alright, C. Determine the length of the path traveled by point E, which I've just highlighted in blue actually, from the beginning of its first move, to when the square BCDE first returns to its original position. So D coincides with Z, and XZ lies along ED. Okay, so we just followed D to Y. So here's where I'd start C. After an 8th move, rotating about Y, which happens to be D, we will get DE coinciding or DE and a line of the DE contains a side of the triangle. Okay. Now, from the perspective of from the perspective of us, this is not the same starting position, because look at the orientation of the original square. The square has rotated, but it's essentially the same picture, just everything, it's just this starting picture has sort of been physically moved, triangle included, rotated a bit. The labels have changed. So it takes it takes 8 moves for D to get back to a vertex of the triangle with DE lying on a side of the triangle. This should happen every 8 moves. Okay? It changes which vertex D is in. So let's say, so every 8 moves, D is on a vertex again, and a side of the triangle coincides with DE. Okay, I would say that's a reasonable thing to say. So, D is at X. No, D is at Z. D starts at Z. Then 8 moves. D and Y are the same. 8 moves, D and Z are the same. Or, sorry, D and X are the same. And then do another 8 moves. So 24 moves, D and Z will be back to the same. And DE. So DE starts with XZ. After 8 moves, DE will be on YZ. Let's say ZY. Actually, I'm going to change it so the D's and the E's line up. So DE is at ZX. Now, E is where Z is, essentially. D is where Y is. 8 moves. D goes to X. E goes to Y. I mean, E is not matching up with Y, but E and Y are in the same sort of direction from D and X, which coincide. And so 8 moves again. DE will coincide with ZX. Okay. So it takes 24 moves. Does that mean I need to draw 24 pictures, or rather 16 more pictures? I don't think so. It's the same journey every 8 moves, just told from sort of a different perspective, but E doesn't care how we are viewing this particular picture. So I think we can say distance E travels is 3 times distance E travels in 8 moves. That seems reasonable. Incidentally, there might be some sort of fix E and see how the triangle moves sort of way to do this. I'm not entirely sure what that would be, but there might be a way to do it. Instead, I'm just going to sort of go back to my pictures. You can redraw pictures if you want to. But what happens in the first little bit? E rotates 120 degrees, and this is a circle of radius 1. So E moves along the circumference of a circle of radius 1 by 120 degrees. So a third of the circumference of the circle. Circumference of the circle is 2 pi r. In this case, r is 1. So that's how far E has moved in the first step. So 1/3, 2 pi r. Then E stays in the same place. And then what happens? E moves down here as this part moves up to join X. So E moves another 120 degrees. So that's another third. So 2 pi and 1. So another third of the circumference. On the next step, E still moves. How much does my square rotate? About X. That's the one it's rotating around this time. It rotates 30 degrees because we've got 60 degrees and the full corner is 90 degrees. So E only moves down by 30 degrees. But it's rotating around X. So that's going to be a distance of 2. So 30 degrees is 1/12. So we'll have 1/12 of a circumference, but now the radius is 2. Okay. I'll write all this out a little nicer and neater, but I'm just trying to understand what's going on. Now we're rotating around Y. So how far is Y away? So that'd be 1 and 2. So 1 squared plus 2 squared is 5. So a distance of root 5. E is root 5 away from Y. And how much are we rotating? 120 degrees, I think. Yeah, we rotate around Y till this corner matches up with Z. But it's E that we're concerned with, so E rotates root 5. And it's another 120, so 1/3 the circumference, but now the radius is root 5. Okay. Then again, we got another 30 degrees. We technically had 30 degrees here, but the radius, the distance from E to the center of rotation, well, E coincided, so it was a radius of 0. And now we're rotating about Z. Distance from E to Z is well, it's on the opposite side of the triangle. So 2, 2, so it'll be 2 root 2, and we're rotating 30 degrees. So 1/12, 2 pi, and a radius of 2 root 2 this time. Okay. So I'm getting the hang of this, I think. And now we rotate around x, which we are a distance root 5 from. And we need to rotate 120 because this is d coming back to y. So it'll be 120 degrees, so that's a third of the circumference. 2 pi, and my radius is root 5. And now the last step, 30 degrees downwards. Does that make sense? Yeah, okay. So so E comes down by 30 degrees, and how far is it away from Y, the one we're rotating around? A distance 2. So that'll be 1/12, 30 degrees. So 1/12 of the circumference, 2 pi and 2. So let me write that up. So move 1. E rotates 120 degrees. Distance 1 from the center of rotation, let's say. Move 2. E rotates 30 degrees. Then it'll be another 120 degrees. Move 3, move 4, move 5, move 6, move 7, and move 8. And it just seemed to alternate 30 degrees, 120 degrees, 30 degrees, 120 degrees, 30 degrees for the last one. And then it was a distance of 0 from the center. And then the next one was a distance of 1 from the center. And then a distance of 2 from the center. Now it's 2 away from x. Distance 1, then distance 2. Then it was distance root 5. Then it was the furthest it ever is away, and that's a root 8, or 2 root 2. And then a distance root 5, and then another distance of 2. So it goes 0, 1, 2, root 5, root 8, and then it goes down, root 5, 2, 1, 0. That's sort of what's happening here. Okay. So E travels, let's see, 1/3 a circumference of 1 plus 1/12 a circumference of 0 plus 1/3 a circumference of 1 of a circle of radius 1 plus 1/12 a circle of radius 2 plus 1/3 a circle of radius root 5 1/12 a circle of radius root 8 plus 1/3 a circle of radius root 5 1/12 a circle of radius 2. Alright, I think I got that, and then it does that 3 times. Because it'll go back to being a distance 1 away from our new axis of rotation, which will be z rather than the x that we started with the first time. Okay, let's take out a factor of 2 pi. 1/3, 0, 1/3, 1/6. Actually, let's put everything over 12. That might be easiest. So 1/3 is 4/12, 0/12, 4/12, 2 over 12, 4 root 5 over 12, root 8 over 12, or 2 root 2, whatever you want to say. 4 root 5 over 12, and then 2 over 12. Again. Alright, so, and this will be 3 times all of that. So we'll change that to 6 times all that. And that way the 6 can cancel out with some of the 12. So I'll have pi 4 over 2, 4 over 2, 2 over 2. Actually, let's just say pi by 2. Pi by 2, we'll say 4 plus 0 plus 4 plus 2 plus 4 root 5 plus root 8 plus 4 root 5 plus 2. 4 and 4 is 8 plus 2 and 2 is 12. And then 8 root 5 12 plus 8 root 5 plus root 8, I guess. Or we could change that to 2 root 2, can't we? And then we could finally get rid of this 2 that we're dividing by. So it'll be pi times 6, 4 root 5 plus root 2. And that should be the distance traveled by E, and there's nothing simpler I can do with that. No fancy way to write that nicer, but there it is. So that's our answer, and that finishes off our 2015 Galois paper. It's been a good paper, I would say. Can't wait to see the 2016 paper, but that will have to wait for another day. So thank you guys so much for watching. If you want to keep up to date, for example, when I do the 2016 Galois, or any other Galois or any other papers, feel free to throw down a subscribe or click the subscribe button and make sure the notification's on or whatever it is. If you have a different way to do a question, maybe you found a way to do what was it? Sort of fix E and have the triangle move around. Maybe you had a nice way to do that. I would absolutely love to read it. So if you want to throw a comment down below, feel free to do so. But I am going to take a nice little break, and I will see you for more math in whatever future video you decide to watch. I'll see you there.